Hello, everyone. Thank you for coming. Thank you. Thank you. Thank you. I'm monochrome. For these several years, I'm working on my implementation of Ruby. It is named MonoRuby. In the last RubyKaigi, I presented an overview of MonoRuby. And this time, I want to talk about how it works and how to make it faster. So, first of all, let me introduce myself. I am a general surgeon. My specialty is the detection and treatment of cancer in the digestive organs, and like gastric cancer and colon cancer. It's kind of a hardware engineer of human body, having a national license. I have a national license that allows me to debug or fix or cut or stitch human beings. And I also love Ruby and Rust and JIT compiler. So I'd like to mention about my personal connection to this Matsuyama city. And Matsuyama is where my grandmother was born. And my father spent his childhood. And of course, my grandmother passed away many years ago. My father is 91 years old and doing well so far and plays golf 3 times a week. And while his son is sitting all day long and writing compiler and assembly, he's not healthy. So let's get started. And this is about MonoRuby, and this is GitHub. This is GitHub, and it consists of yet another Ruby parser, and garbage collector, and interpreter. And parser is very annoying, and we want to go to prison someday. So we have some progress, and now Ruby gems is supported, and we can require gems. And now, struggling with bundler. Yes. And we must mention about compatibility with CRuby. Of course, there is a bunch of things to do. Many classes and methods are missing. But here, especially for the functionalities which affects performance, we support bignum and fiber and binding, and redefining basic operations methods like integer add. On the other hand, we do not support C extensions. This is a big problem for now. Native threads, thread classes, and Raptor, we do not support them. We also do not support object space, trace point, and refinements, and callcc. And callcc will never be supported in the future. I'm sorry. And this is micro benchmark with widget bench and showing ratio to CRuby 342. And red bar shows MonoRuby. It shows 3 to 10 times faster than CRuby interpreter. And this pink bar shows a MonoRuby interpreter. It's comparable to CRuby interpreter. Benchmark on opt-count. This shows a frame per second over time. This is start point, and time goes. And red line shows a MonoRuby. It achieves 6 or 7 times faster than interpreters. Interpreters is here, this pink and light blue lines. And this blue line is widget. And the green lines are TruffleRuby, showing a slow startup and nice peak performance. And we have several build options for debugging and profiling. This is a profile option that we can see stats for de-optimization and recompilation and method cache failure, and so on. And another option, deopt, we can check when, where, and why the optimization occurred. This shows the layout of bytecode. I'm sorry. And our bytecode it's 16 or 32 bytes long for one instruction. This is add instruction, and this is opcode. This is operands, Operands means a register number of a left-hand side and the right-hand side and destination. And for method call, this opcode and operands like receiver and arguments and the number of arguments and destination. So take a look at the blue part. This blue part. There are trace informations attached in the bytecodes. They are collected by interpreter. So for add instruction, there's a class ID of left-hand side and right-hand side. For method call, there is a receiver's class and the method call and method version. So it means a kind of inline method cache. And this is a class of receiver and ID of a callee method are stored there. So this is structure of stack frame. And if you call a certain method block, each stack frame is pushed, and the frame is popped when you return. The frame has a link to the caller frame, like a chain, and also have a link to a local frame. This is local frame. A local frame holds the self, this register 0, and arguments and local variables and temporaries, and the block given and some metadata. It also has a link to the outer scope, like this. And local frames are mostly placed on the stack and push and pop. But if proc or binding object was made inside the frame, the local frame is copied, like this, copied to heap for persistence. And this is how the interpreter and JIT compiler and generated JIT code work. This is interpreter, fetch the bytecode, and dispatch, and the execute. And this is an infinite loop. And if many times a certain method called, or and many times a certain loop executed, we compile the bytecode to the machine code. It's a JIT code, and just jump them. And this is a JIT code, and JIT code is compiled with some assumption. Assumption means this method call, the receiver must the class A, and the Ruby is a dynamic language, so these assumptions sometimes breaks. If assumption breaks, we must de-optimize. De-optimize means fall back to interpreter and do it again. Yes. So JIT compiler is an extremely complex system, and the only one thing that justifies its complexity is performance. So we must generate a nice code. And there are several hardware resources that CPU can use. There's a stack in main memory, which is slow, and register the CPU, which is fast. In the x86 CPU, roughly two categories of registers are there: general purpose registers and floating point registers. We must use floating point registers to calculate floating point. And in the interpreter, the value of each register is stored in stack. It's 1-to-1. It's simple. But in compiler, for optimization, we must track the state of each register. A state means where the value of the register stored in runtime. It may be stack, like this. It may be a CPU register, like this, or floating point register, like this. So we must track where the value of the register is stored, actually. And it is necessary to generate code for storing the value in anywhere. Just record in the state, like this. If compiler knows the value of register, like a literal, float literal, in compile time, it is necessary to generate code for storing the value, and we must just record in the state. So think about a small method area which calculates the circle area for a circle with radius r. And you are a JIT compiler. At first, an argument r is stored in register 1, but compiler does not know what it is. It may be integer or float, and can be string. So it is colored in gray. So next, multiply operation, and trace information shows register 1 is an integer. So we must check the value of register 1 are actually integer. This is. After checking, we know register 1 is integer. So register 1 is colored in yellow. This is integer. Yes. And multiply register 1 by itself and got the integer result here and stored in the general purpose register R15. So we must check the result. If overflow occurred, we must de-optimize and fall back to interpreter and do it again. Check the overflow. If no overflow occurs, link register 2 to this R15 register. Next, load liter of 3.14 to register 3. We know it is a float. Okay. So just change the state. No code is generated. Just link register 3 to 3.14. Multiply again. And now we know register 2 is an integer. This is colored yellow. And register 3 is float and colored blue. And we can omit guards for both sides. So we must load the values to floating-point registers for calculations, like this. Here, multiply XMM2 by XMM3 and store the result in XMM4. Of course, we know all of them are float, so colored in blue. Link the returned register is number 2, so we must link register 2 to XMM4. And finally, we must return with register 2. But register 2 is stored in XMM4, it's float, and we must convert from float to Ruby value, 3.4.0. So we must convert and return. Well done. Yes. This is another topic for optimization. It's specialization. Think about a method RH. The problem is we cannot know which block is given from caller, and so we cannot know a signature of a given block. A signature means details of parameters that methods or block have. It means how many positional arguments on optional arguments and what kind of keyword arguments. It is necessary to know the caller's number of arguments and call is parametered in compile time for an efficient code generation. Otherwise, we must do a lot of things in runtime. So the idea is the caller method and method like RH and block. We compile them all at once and write RH itself in Ruby, not Rust, to use trace information efficiently. This is an RH in Ruby, and this is bytecode, and this is call for graph. And look at this. There's a block giving. This is method, but we can optimize this using an inline assembly. This is a code for kernel block given, and it's the last code, sorry. And if we know the block is given in this specific specialization, no code is generated. Just change the state. So if not, we can generate assembler directory. So in this specialized context, we know the block given is always true. So we can remove these instructions and these conditional branches and this basic block itself. There's another method, array size or array index. We can we can substitute inline assembly. So generally, the last thing is yield. And yield is very slow because we cannot know which block is given in compile time, and we cannot know the signature of callee. And we must use indirect branch. It suffers branch predictor of CPU. But in this specialized context, we know the signature of callee block in compile time, so we can generate efficient code. So this is a benchmark for specialization. And this shows kilo iteration per second. The higher, the better. These are various methods like integer times or integer step or array, array map. And the red bar shows a monoruby, and the blue bar shows cruby 342. Yes. And pink lines shows monoruby without this optimization. So you can see the improvement in performance. And in this red bar, monoruby, methods are written like RH are written in Ruby. And in pink bar, before optimization, methods are written in Rust. So on the other hand, green bars are for interpreter, shows getting slower after optimization. So I show some demos. This is some idiomatic Ruby code. We execute this. Like this. Thank you very much. Thank you. So enjoy the rest of RubyKaigi. Thank you very much.